Okay, topic of this concept, enzymes. So, enzymes are a type of protein that speed up biochemical reactions by lowering the activation energy. So, because they speed up reactions, they are called catalysts. So, when an enzyme catalyzes a reaction, it is just speeding it up, it is aiding it along. And so, if we think back to those energy diagrams, by lowering activation energy, we're really just lowering the amount required. So, remember, there was that whole mountain needed in order to begin that reaction. Enzymes would catalyze it and would only require maybe that much energy before the reaction would take place. So it would lower the amount needed. And so what are enzymes? Enzymes are specialized molecules that bind to reactants, so remember the left side of the equation, and help to break or form bonds. And then they release a newly created product. And then just one really important tidbit, enzymes are not changed in a reaction and can be used over and over and over again. Okay, let's put this down here again. Okay, so enzymes are very specific. So here's an example of an enzyme, and they have this thing called an active site that only fits one substrate or reactant, so it only fits one type of substance. And so this is the active site that I was referring to, and it's basically just kind of like a very specific shape that only one type of molecule can fit. And so this is what it looks like, a substrate or a reactant fitting into the active site of this enzyme. And this diagram, this image, this idea right here is known as the lock and key model. So there is one key for that enzyme that kind of opens the lock and allows that reaction to occur. So let's look at some diagrams. So this is an example of an enzyme in 3 different stages, moving from the left to the right. So on the left, we have our substrate binding to the active site of our enzyme. And then the bonds break between the atoms of this molecule. And then at the end of the reaction, the catalyzed reaction, you end up with these 2 products on the right. So this is an example of an enzyme catalyzing a reaction in which the molecules' bonds were broken, so it was broken apart. So enzymes can break bonds on a substrate to form 2 products. Then the other kind of enzymatic catalyzation is when enzymes make bonds between substrates to form one product. So here's our enzyme again with our active site, same active site. And then we have these 2 substrates that kind of fit in that enzyme like a lock, like a key would fit into a lock. Those bonds are formed between those atoms within those molecules. And then we have one final product. Okay, so what happens when the shape of an enzyme changes? Can we still have that lock and key model if our lock is disfigured? And so this idea is known as denaturation of an enzyme. And so this occurs when an enzyme's active site gets deformed and loses its specific shape. And so we say that this causes a loss of biological activity. So our body is able to do less things biologically when our enzymes are denatured. And so this can be caused by a variety of things. It can be caused by extreme changes in pH, temperature, ion strength, and solubility. So there's a few different things that happen. And although enzymes can always be renatured to their original, not always, they can be renatured to their original shape. They can't always. So sometimes it's fixable and other times it's not. So yeah, obviously normal enzyme on the left, our denatured one on the right. Okay, so there are a few ways to change the speed at which a chemical reaction occurs. And the first way is by altering the temperature. So if you increase the temperature or decrease the temperature of a chemical reaction of the environment that it is occurring in, you can affect that rate. So when you increase the temperature, you increase the rate of the reaction because those molecules are moving faster and are colliding more with each other. If you recall from that one video from Unit 1, when I talked about particles of different states, solids, liquids, and gases, and how solids are much more, their atoms are much more tightly packed together. But when you increase the temperature of any kind of substance, those atoms, those particles, even if it's a solid, are like vibrating against each other, moving faster, and they're hitting each other more often. And so that will definitely affect how fast a chemical reaction occurs. And just think about gaseous particles. So they have tons of space to kind of freely flow around each other. And so when you increase the temperature of a gas, those particles are flying around left and right, and they're hitting each other, colliding each other with a lot of force. Then the second way to change the rate of a chemical reaction is to change the environment's pH. So that just refers to how acidic a solution is. And so much like how I really enjoy having my house at 72 degrees, most enzymes only work at very specific pH levels. So if that pH changes, the reaction speed can be affected. They're not going to want to do very much work when they're not in their ideal conditions. The third way to change the rate of a chemical reaction is by changing the concentration of the substrate. So by increasing or decreasing the amount of reactant available. So the higher the amount of substrate, the faster the reaction is going to occur. So think of it like this. You are much more likely to hit and collide with another person when you are exiting into a crowded room. You're probably going to brush up against someone, or someone's going to hit you, or you're going to have do that awkward like little dance where like you almost hit each other, and then like you both like go that other way, and then like you laugh and you're like, okay, and then I'll go this way, and you guys both go that way, and you have another laugh, and you're like, okay, cool, let's stop being weird, I just need to get where I'm going. So that's a lot more likely to happen. Whereas if there was no one else in the room, you could just walk right on through. And so there is a lot less of a chance of a chemical reaction occurring if there is less reactants around. So it has to do with particle collisions. Then the fourth way to change the rate of a chemical reaction is by using a catalyst, which is what we've been talking about, like an enzyme, to speed up a reaction. And it does this by lowering the activation energy needed for that reaction to start. So remember that kid rolling down the hill? Maybe somebody else pushed him, basically. Or, I don't know, the wind just like kind of pushed him and it helped him, so he didn't have to use any of his own energy. Okay, and then the fifth way to change the rate is by when a competitive inhibitor is introduced. And so this, when this occurs, the reaction is slowed down. And so this is when there is another particle or substance competing with the substrate for the active site on the enzyme. So if we think about that lock and key model, let's say that someone made a copy of your key, but it's not. It fits in the lock, but it doesn't do anything. It doesn't open the door. It doesn't turn anything on. All it does is it takes up the space so that another key can't enter, so that the correct key cannot enter, turn the lock, and then you can open the door and get inside your house. It just kind of is taking up space, and it is competing for that active site. It is inhibiting the reaction by taking up the spot that is supposed to be reserved for the substrate or reactant, for the correct key for that lock. Who cares? So I always like making sure that we connect this to why the heck do we care about this and why are we talking about this? So a fundamental task of proteins is to act as enzymes or catalysts that increase the rate of virtually all the reactions within our cells. And so if we did not have these enzymatic catalysts, most biochemical reactions are so slow that they would not occur under the mild conditions of temperature and pressure that are compatible with life. Enzymes accelerate the rates of such reactions by well over 1 millionfold. So reactions that would take years in the absence of any of these enzymes can occur in fractions of seconds if catalyzed by the appropriate enzyme. So our cells contain thousands of different enzymes. And one example that I can tell you to maybe help solidify this for you in your brain is to think about the process of how we digest our proteins, how we break down the proteins that we eat into something that can be used by our body. So you go to In-N-Out, you get that burger, you eat it, it goes down into your stomach, into your small intestine, and what happens? So there is an enzyme called chymotrypsin, and it is an enzyme that helps facilitate the reactions of the hydrolysis or breakdown using water of peptide molecules, of proteins. So just think about putting some protein in a cup of water and like sitting and staring at it. It's probably not going to do anything. However, to your shock and surprise, if left there for long enough, eventually those proteins would break down and would be hydrolyzed. The water would break apart those peptide bonds, and they would be made up of smaller little protein fragments. However, that takes forever and it is really inefficient. So our bodies have found a way around this, and through the production of enzymes, the creation of enzymes, or the utilization of enzymes, we are able to speed up those reactions in fractions of the time, because we would die if we were waiting that long for the reactions in our body to take place. We ate that protein, we ate that In-N-Out burger. I need that protein now, or at least today, not in a million years. So the enzymes are very, very, very important to the maintenance of homeostasis within our bodies. They are very important in our cells, and they allow us to remain alive. So that is why you should care about enzymes.